que comienzo a este tercer DISI. Primero que nada, thank you so much for being here, Radia. It's a pleasure. And welcome to Spain and welcome to the Polytechnic University of Madrid. Now I'm going to introduce you a little words in Spanish, so if you can use the headphones. Thank you so much. Bien, un breve currículum solamente de Radia, o Radia en inglés, ¿no? Radia George Perlman es PhD en Computer Science desde 1988 por el Massachusetts Institute of Technology, precisamente el mismo año en que la ACM propone celebrar el 30 de noviembre como el Computer Security Day. Es autora de 2 libros sobre seguridad en redes, justamente los tenemos aquí. Uno es Interconnection, second edition, y el siguiente es Network Security, Private Communication in a Public World. Y además una de sus más conocidas contribuciones ha sido el invento del Spanning Tree Protocol cuando trabajaba en Digital Equipment Corporation. En la actualidad trabaja en Sun Microsystems. Con más de 50 patentes ha impartido clases en el MIT, en la Universidad de Harvard y en el Swedish Royal Institute of Technology. Ha sido considerada en 2 ocasiones como una de las 20 personas más influyentes en el ámbito de las tecnologías de la información por la revista Data Communications. En 2004 gana el premio Silicon Valley Inventor of the Year. En 2005 fue galardonada con el Women of Vision Award for Innovation, distinción otorgada por el Instituto Anita Borg a las mujeres que más han contribuido al avance tecnológico de la humanidad. La doctora Radia Perlman nos presentará la conferencia titulada Adventures in Network Security. Radia, 21. Okay. Por favor, la gente de sonido que esté aquí.
Adventures in network security. One of the things that I would like people to understand is that in the world of protocols, not everything published is correct. So if you find papers in a journal, it doesn't mean that just because it got published, you should believe it. Also, the standards are not necessarily good. They're designed by committee. Everything is very political. So it's not necessarily the best technology that wins. Yeah, as I said, it's distressingly political. Sometimes you go up to a committee with an argument saying, your protocol won't work that well in this case. If you change it this way, it will be a lot more efficient. And they sometimes look at you and they say, you're ugly. You know, it's like, that might be true, but can we stick with the technical argument? Also, something I find kind of annoying is how in universities, often the way they teach networking is to make you memorize what happens to be deployed, rather than teaching you to think about it critically. So they teach you to say, here are the fields in the TCP and IP header, but they don't teach you to think that a particular problem could have been solved in 7 different ways, and here are the critical trade-offs, what might have been better, or also to know that there have been other protocols, and to understand how they compare, I think is a lot more interesting than just knowing how to implement what happens to be standardized. And what would be much more interesting and empowering to students is to show them bad papers and, well, to teach conceptually so that they understand that the people who are designing these protocols don't always do the right thing, and so that it just makes them feel like, yes, they could make a contribution. Also, rather than just having them read good papers, have them read bad papers from good conferences. And that way, they can realize that, it's not that a different species of person manages to publish papers. Also, there's a lot of really good papers that have been rejected many times. So if you find some of those papers and explain to people, this is one of the most fundamental papers, but it was rejected 4 times. So yeah, I mean, one of my favorite rejections of one of my papers was on an improvement to my thesis. So the paper that I wrote, which I submitted anonymously because you are required to, the way the paper read, it said, Perlman's thesis works like this. It doesn't work in certain cases because of these problems, and we'll fix that in this paper. And so one of the reviewers said, you've completely misunderstood Perlman's thesis. It does work in those cases, and you know, that's a terrible paper. So on the one hand, it was very sweet because I could tell that the reviewer was defending me, defending my honor, because they felt like the paper was criticizing my work, but it would have been nice to get the paper accepted. So I will give you an example of interesting kinds of things that might be taught. So yes, you have to teach cryptography because you need to know it, but a lot of times courses get too excited about the very theoretical kinds of things and all of the math and all of the proofs. And I don't think that's the really interesting part. I don't think the world needs more cryptographers. They need more people that understand how to use cryptography. So I'll give you an example of something that, even though it's about cryptographic protocols, is not about cryptography. So here's an example type of issue that I think is very interesting for a class. So the question is, what's the difference between the protocol SSL, which is also called TLS, or IPsec? So how many people have heard of IPsec? Okay, and SSL you use all the time, so hopefully you know that. So let me tell you what the difference is between them. They both sound the same. Both of those are protocols designed to have 2 people figure out who the other one is, authenticate the other one, and then establish a cryptographic key and encrypt the remainder of their conversation. So both SSL and IPsec do that. So what is different about them? Well, the protocols look different because they were designed by different committees, but that's not the interesting difference. So the difference is one is layer 3 and one is layer 4. Well, great. Now if you're taking a quiz, you know what to write down as the answer. But what does it really mean that one is layer 3 and one is layer 4, and why should you care? What difference does it make? And so I'm about to explain that. Okay. So IPsec is at layer 3. What that means is their idea was, let's do security once within the operating system and automatically protect everything. So we won't require any changes to the API, to the applications, and no changes to the application.
So by doing the work once within the operating system, you've automatically protected everything. The philosophy of the layer 4 was, let's not change the operating system and only deploy it as a user-level process. And so by definition, what's inside the operating system is TCP and everything below it. So SSL works on top of TCP, and TCP is unchanged. It has no idea that any cryptography is going on. So what is the functional difference? Well, the layer 3 approach, IPsec, has a very important technical advantage. Because if you're doing it the other way, on top of TCP, TCP is unaware that any cryptography is going on. So it's very easy for a bad guy to send a packet that looks okay to TCP. And once TCP accepts a certain portion of the address space, of the byte stream, because someone can there's no cryptography preventing you from doing that, the real data can't get through. And so even if SSL could tell that this happened, there's no way for it to tell TCP, whoops, that was bad data, so throw it away and give me the good stuff. So it means that with this approach working on top of TCP, with a single packet, someone can break your connection and make you have to hang up and start the connection again. Whereas with IPsec, every individual packet is separately cryptographically protected. So it's sort of a better way to do it. But there's always lots of buts. If you don't change the application, if you're just doing IPsec inside the kernel, the problem is that IPsec will authenticate you with all these fancy things like certificates. And so your machine might know that it's talking to radia.perlman.sun.com, but the API from IP upwards just says what IP address it is. So all of this fancy authentication doesn't do you any good because the application can't be told that IPsec figured out it's talking to Radia Perlman. All IPsec can say is, I'm talking to IP address 79. So the ideal solution is where you actually do change the applications and the API so that you can pass up who you actually authenticated. So another topic is how to use public keys and avoid all of the advantages. So in order to appreciate this example, and this is an example that was deployed by a major company, and so there's a lot of people that use cryptography in their protocols, but if you don't really understand what you're doing, even if the mathematics is correct, you can get a system that's not secure. So this was a great example of one of those systems. So first, in order to appreciate this example, I have to explain what kind of advantages you should expect when you're basing a system on public keys versus secret keys. So, okay. So with key distribution, with secret keys, there's a single key between two users, and you ideally have a different key with every pair of users. So if I talk to Alice, I would have a different secret key to protect our conversation than if I was talking to Bob. So that's basically how secret keys work. Now, how would it work on the internet? You don't want to have to configure a different key for every possible user you would want to talk to. So the way that it's done is with a magic box, which is known as a key distribution center, a KDC. I mean, in the Microsoft world, it's called the, I forget. Whatever, it's called different things in different worlds. The domain controller in Microsoft, and in Kerberos it's called KDC. The idea is that you have this box that knows one key for each user, and then each user only needs to know a single key, which is the one that it shares with the box. So the box knows that Alice's key is key sub A, and Bob's key is key sub B, and Bob only has to know his own key. So this is great. Everybody can talk to the KDC, but who wants to talk to the KDC? The problem is that Alice wants to talk to Bob. And the way this is done is that when Alice wants to talk to Bob, she asks the KDC to introduce them. She sends a message to the KDC saying Alice would like to talk to Bob, and the KDC invents a new key for them to share and can securely send a message to Alice encrypted with K sub A saying, if you want to talk to Bob, use K sub AB, which is the key it just invented, and it can send a message to Bob saying, if you want to talk to Alice, use the key K sub AB, and now Alice and Bob share a key. Alice sends a message saying she wants to talk to Bob. The KDC invents a new secret and sends a message to each one of them saying what the shared secret will be. Now, in contrast, let's look at how you would do it with public keys. Now, with public keys, it's sort of this magic technology where each user has a pair of secrets which are inverses of each other. So everybody has only a single pair of keys, one half that they tell the world, the public key, and the other one, the private key, that they keep secret. Now, this is kind of frightening when you first hear about it, because you think, how can it possibly be secure for me to tell you my public key and you can't figure out the inverse number, the private key? So I'll tell you, well, it's just special math where it's impossible to find one number from the other. And then you're feeling happy for about 5 seconds, and then you go, wait a minute, if you can't find one number from the other, how did you get these two numbers? And that's a wonderful story, how it can be done, but we only have an hour now, so but at any rate, the notion is, so when people think, when they first see public key, they think, wow, we don't have the hard problem of distributing keys like we do with the secret key world, because your public key, you don't want it to be secret. You want everybody to know your public key. But the problem is, how do you know if somebody makes a billboard and says, Radia's key is 75? How do you know it was really me that put that billboard up? If somebody can trick you into thinking that a public key belongs to me when it doesn't, then they could sign a message and you would think it came from Radia when it didn't. Or they could trick you into encrypting a message that they can read. So you have just as much a problem. So the way that's solved in the public key world is that you have this a service which is known as a CA, or a certification authority, which digitally signs with its private key a message that says, it's called the certificate. Whoops, that says, I say that this number is Radia's public key. So if everybody has gotten a certificate from the CA, and if everybody knows their own private key, and they know the CA's public key, then they can authenticate. And it works like this. If Alice and Bob want to talk to each other, Alice sends sends her certificate to Bob. Bob, because he knows the CA's public key, can verify this signature and believe that Alice's key is that number. And Bob sends his certificate to Alice, and likewise, she verifies the signature of the CA. And now they know each other's public key and their own private key, and they can authenticate and encrypt and all that. So now the question is, what's the functional difference? Both of these systems work, but why would you prefer one over the other? So the KDC solution, that's with the secret keys, is less secure. And why is it less secure? Well, you have this box that has to be on the network. And apparently, for reasons I don't understand, nobody can actually implement anything these days in less than 100 million lines of buggy code. So it will probably have bugs and can be exploited. Whereas the CA is not online, so bad guys can't try to find bugs. Also, the KDC has to be replicated, because if the KDC is down, nobody can talk. Whereas the CA, you get certificates in advance, and you don't need the CA to be there when you actually talk. So the KDC, you have to have a lot of different ones, because if one is down, you need another one, and every one of them has to be physically secured, or else somebody could break into it. It also, the KDC solution has a highly sensitive database because it knows everybody's secrets. Whereas the CA doesn't need to know anybody's secrets. It just certifies their public key. The KDC solution will also be more expensive because it has to have a replicated, performance-sensitive, complicated box, whereas the CA is just like a calculator. You can lock it in a safe, and every once in a while it creates a certificate. If it takes it 20 minutes to create a certificate, you probably won't care. It certainly won't take that long. Okay, so the summary of it is the difference between public key and secret key is that with secret key, having this extra box, the KDC, is a security problem because it knows everybody's secrets and it's sitting right there on the net. It's a performance problem because you have to talk to something first before Alice and Bob can talk to each other. It's an availability problem because if it's down, then you can't talk. And it's a privacy problem because it knows everything that you talk to. So now let's look at a system that was deployed based on public keys, and yet they managed to avoid any advantages. So how did this system work? Let's see, I think it's better if I just, okay, so the way that it works, I'll use the picture, is Alice wants to talk to a server, Bob. There's a directory that knows everybody's public keys. So when Alice says to Bob, I want to talk to you, Bob goes to the directory and says, what's Alice's public key? And the directory answers, this is her public key, and then they can authenticate. So what's wrong with this? The directory is not storing a certificate. It's just storing the public key. So now it's an online box that if somebody were to break into it, it could impersonate all the users by giving out bad public keys. Also, just like with the KDC, Alice and Bob can't talk until there's this extra conversation going on. And also, if the directory is down, it has the availability problem. So it has all of the disadvantages, except maybe that the directory doesn't have to know Alice's private key. It just needs to know her public key. But they were creative enough to avoid that advantage as well. And the way that the mistake they made there is that how does Alice know her own private key? If you carried around on a smart card, then that would be fine. But this was done before anybody had smart cards. So they had a very nice user interface, which was that the directory stored Alice's private key encrypted with her password. And when you walk up to a workstation, you first download your private key from the directory, you decrypt it with your password, and then your workstation knows your private key. But it's a little bit insecure to let everybody download Alice's private key because they can do a dictionary attack if Alice doesn't have a very good password and decrypt her private key. So they first made you prove you knew the password. So there was some sort of protocol where you had to prove to the directory that you knew the password before it would download your private key. So that's fine, but in order to do that, the directory had to store some sort of quantity X, which is some sort of hash of your password, so that you can have a protocol to prove that you know your password. And they also stored your private key encrypted with some function of your password. The problem was they used the exact same function here. They should have used a different function of the password. But what they stored was some quantity X, which was a hash of your password, and your private key encrypted with X. So if somebody stole the server database, they would directly know everybody's private key, because you just take this number and decrypt it with that number, and it's as if they were storing all of the private keys unencrypted. Okay, so now I'm going to switch to something else, which is to tell you something I'm working on, just to give you an example of kind of interesting things that you can work on when you're in industry. You don't have to be at a university in order to be doing interesting research. Now, I don't do things that, because I work for a company, I can't just write papers that are, of purely theoretical interest. I have to work on things that might actually be useful. But I don't find that to be at all limiting. I find real problems much more fun than problems that all you get out of it is an obscure paper that you can put on your resume. So the thing that I'll talk about is one of my projects. It's how to get rid of data. So the problem is that you want to be able to make a lot of copies of your data so you don't accidentally lose it, but you want to be able to make sure that it's gone when you really want to make it be gone. So there's the problem that in order not to lose it accidentally, you want to make a lot of copies. But once you make a lot of copies of the data, you can't store every one of them in a place with a guard. You'll lose control over it, and somebody can steal the backup copies. So once you've made backup copies, you can't assume that if you want to get rid of a file, you can find all the copies of it and get rid of it. So that's not going to be the solution. So we're going to solve both problems, that we're going to make a file really be gone when you want it to be gone, but yet be able to make as many copies of it as you want so you don't accidentally lose it. So the obvious approach is that you encrypt the data and all the backups are encrypted, and then you throw away the key when you want the file to be gone. But the problem is you have the same problem with the keys. You would have to make copies of the keys and then destroy the keys. So even though it might be easier to manage the keys than to manage the data, it's still going to be hard to manage ephemeral keys, where ephemeral means you want to get rid of them at some point. So in theory, this would work. If Alice wants to send a message to Bob that she wants to have it expire in 2 weeks, Bob could have a whole bunch of public keys and promise to throw away the private key of each public key at a specific time. So she would encrypt it with the public key of Bob that he intends to throw away the private key in 2 weeks. But there's a problem with that, and here I just sort of use a quote from my book to show you that a textbook on cryptography and network security protocols can also be fun. So the problem is humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It's astonishing that these devices continue to be manufactured, but they're sufficiently pervasive that we must design our protocols around their limitations. So the problem is we have to design something that's really easy to manage. So it's unrealistic to expect Bob to manage all of those keys. So instead, we're going to use a service that I call an ephemerizer, because it makes things ephemeral. So the ephemerizer creates a whole bunch of public keys, and it promises to throw away the private key at the right time, and it will decrypt for you. It will unlock its public key using the private key, as long as it remembers the private key. But once it destroys the private key, then it can't unlock it for you. So the basic idea is you're going to take your backup and you're going to put this extra lock on it, which is the ephemerizer's key, which can be unlocked until the expiration date, and after that you can't unlock it anymore because it won't be able to help you. So one application of this is to, when you create a file, you can say, I want this to go away in 1 year. Now, why would you want that? Well, there might be health records, and you might say, for privacy reasons, after you take an AIDS test, they will hold the results for 2 weeks to let you call in, but then after that, all information associated with it will go away. Or corporate email. Some corporations want to be able to say that they only hold email for 1 year, and after that, it goes away. So in case they get sued and told to find all emails that mention the company Microsoft, let's say, then they could say, we only can search 1 year back, which just makes it easier because you don't have to prove you've looked for all of the backups. So the basic idea is that if you have a secure file system, what the ephemerizer is doing is adding an extra lock onto the already encrypted backups. Another concept is that, well, what happens if the ephemerizer loses its keys? So we don't want the ephemerizer to make copies of its keys. So rather than trying to use a very robust ephemerizer that made a lot of its copies of its keys so it will never lose it, you can get the same robustness by using a lot of flaky ephemerizers. So if you have a piece of data, rather than just storing it with one ephemerizer's key, you can store it encrypted with 10 ephemerizer keys. And then if any one of them is around, you'll be able to decrypt it. And then there's another piece of subtlety is you are going, as you'll see, the file system will have a very sensitive piece of data encrypted with the ephemerizer's public key. And in order for the ephemerizer to decrypt it, you don't really want to have to trust the ephemerizer. So there's a protocol in there that makes it so that even though the ephemerizer will unlock its lock, it won't get to see what's inside when it unlocks it. And then the other thing is how to organize a file system so there's basically no performance overhead on using this concept. So let's see. Yeah, there's two possible ways an ephemerizer can fail. One is that it goes out of business or loses its keys, and the other is that it cheats and it doesn't forget the private key when it says that it will. So to solve both problems, you do one of these schemes where you break your data into n pieces such that it requires k out of n pieces to recover it. And then if it takes more than one ephemerizer to recover it, if it takes, let's say, 5 ephemerizers, then 4 of them can cheat and not throw away the key. But as long as 5 of them don't, then you'll be able to withstand ephemerizers failing in that way. Okay, so, okay, whoops. So, let's see, I think, oh yeah, so this is how to ask the ephemerizer to decrypt something without having it see what it's decrypting. So Bob has a message here that's encrypted with the ephemerizer's public key number I. It's the one that will expire on, let's say, October 3rd. So what he wants to do is send this encrypted thing saying, please decrypt this thing with your IF public key. And the ephemerizer will decrypt it and send the message back. But the problem is you don't want the ephemerizer to see M, because M is secret information, as you'll see. So what we're going to do is create this concept that I call blind decryption. Now, for those of you into cryptography, you've heard of blind signatures. This is very similar, but we're using decryption. So the idea is that Bob invents two functions, blind and unblind, that are inverses, like encrypt and decrypt, takes this message, applies blind to it, and says to the ephemerizer, apply your private key. And magically, that will get rid of the public key here, but it will be still encrypted with the blind function. Now, if you don't know anything about cryptography, that sounds easy. You have something encrypted, you just encrypt it again, but it's tricky to find functions that you can do in the opposite order. But just believe me that I have a function that works with RSA keys and a function that works with elliptic curve keys, and I think those are the only two public key functions anyone cares about. So that's so with this protocol, it's a very lightweight protocol. The ephemerizer gains no information when it's asked to do a decryption. The protocol is really efficient. It's just a single message back and forth. You don't have to authenticate either side, and you can even decrypt things anonymously. Just send something to the ephemerizer, say, apply your private key. Okay, so now, and running an ephemerizer is fairly simple too. Just generate all of the private keys in tamper-proof, cryptographic smart card kind of thing, and just every day have it throw away the oldest key and generate a new key. And so it's easy enough to manage an ephemerizer that a customer could manage their own ephemerizers, but the problem is that if you don't own enough different buildings, if you're in a state and you're afraid the entire state will get flooded, then it's nice to use a third-party service to run the ephemerizer for you. So now, kind of in the interest of time, I will just go to the picture here. So this is how to organize the file system so that there's no overhead. So what the file system is going to do is divide the files based on expiration dates. I call those classes. So all of the files that have the same expiration date will be encrypted with the same key. So the file system invents a secret key, S1, that all files that want to expire on January 7th, 2009 will be encrypted with S1. So what a file looks like is that it says what the expiration date is in the metadata, and then the file is encrypted with, in this case, S2. And so as long as the file system remembers these class keys, then it doesn't need any ephemerizers. It's just very straightforward. It just reads the file, the header tells it which key to decrypt the file with, and everything works. But the ephemerizers come in with how you make backups of these keys. So you take the first key, S1, and when you're making a backup of it, you encrypt it with this ephemerizer's P1 key, which also has the same expiration date. And if you want to withstand having that ephemerizer die, then you also store S1 encrypted with Q1. And then you have to encrypt one more time with the system administrator secret, so somebody that steals a backup of this will not be able to decrypt your keys and therefore read your data. Okay, so that's basically the idea. And I won't go into the on-demand stuff, which is sort of cool. But and one thing that a lot of people look at this and they say, this is a great solution for digital rights management. So if you're getting a movie and you download it, you can make it go away in a week. This is not a solution to digital rights. It doesn't make digital rights management easier or harder. It's just a completely different thing, because there's nothing in here that prevents you, once you have the plain text, from storing it outside the system. So it's just something that enables you, if you want this feature, to easily make files go away, but it doesn't require it. Okay, so now I'm going to get less technical. I wasn't sure how technical to make the talk, so I decided to have pieces that were at different levels. So this is kind of dessert from the technical stuff. So I'm going to just complain about the internet now. There's some things, I don't know what I did there. There's some things that absolutely should not work, but they do. You know, there's no way they can possibly work, but yet they do. So one example is web search, like Google. If somebody, before that company existed, if I were a venture capitalist and somebody said they wanted to have some sort of system that looked at everything on the internet and categorized it so that you could instantly search the internet for anything on there, I would have said, no way. There's no way this could work technically. And even if it could, there's no financial reason for a company based on this to survive. Just advertising? No way. But it seems to work. And indeed, it's faster for me to find something on the internet than to search my email for something, which is kind of sad. Another thing is Wikipedia, which there's no way that should work. It should be full of just garbage by now, with people just filling it with curse words and graffiti and stuff. But yet Wikipedia tends to be one of the best sources of information about everything. I don't understand it, but somehow it works. Now, there's things that can't possibly be hard, and yet they don't work. So, safely reading email and surfing the web. How can that be hard? How can it possibly be difficult to build a system that lets me read my email without getting my machine infected or searching the web? It's very frustrating. Another thing is user interface. It's like there are so many times when people say, we need to train the users better. And I get really mad every time I hear that. No, you don't. It's not the user's fault. It's whoever is building the system has to design it for the users, not think that you can, make this like URLs. I mean, what were they thinking? You're supposed to look at the certificate and look at the name and the URL extracted from this obscure string, and it's the user's fault that they don't know that if you, have a % in there, that everything to the left of that is ignored. Whenever you hear anybody say, we need to train the users, hit them for me. Authentication. Authentication should be based on public keys. When I saw public keys in the 1980s, it was like, yes, this is going to happen. It still doesn't. We're still using passwords. I do not understand this. It can't be hard. So, why are we using passwords? So now I'll tell you what it's like for me as a user using the internet. So you want to buy something. So as it turns out, you're buying a pair of shoes or something. You've searched, you found the shoes you want, and you decide to buy them. And you forget that you happen to have bought something from that merchant 5 years ago. And so you're all prepared. You know your address, you know your name, you have your credit card out, you're all ready to do it. And then at the end, it asks you for your email address in order to do a confirmation, which you need to do. And you type in your email address, and it says, hey, you're a returning user. Type your username and password. It's like, I don't remember. So now it won't let you buy it until you type your username and password. There's no way to say, I want to bypass that. Treat me like a new user. So with a lot of effort, you can find the place where it says, have you forgotten your username and password? I will help you recover it. And so you find that place and you say, why, yes, I have forgotten. And so suddenly you're in a Monty Python movie where it says, answer the following questions 3. What is your telephone number? And it's like, I don't know. Did I lie because I didn't want you calling me? I moved 6 times. Was it my cell phone? Was it my work phone? What's your address? I don't know. I moved several times. Does capitalization matter? What's your mother's maiden name? Well, I don't know. Did I put in her last name? Because you're talking to a computer at this point. So, new rule. It should be no more onerous to be a returning user than a new user. Why should I be penalized because I bought something from you 5 years ago? Now, when they have security questions for for getting your password or your username, who came up with these questions? So it's like your favorite sports team. It's like, I don't follow sports. Your 2nd grade teacher's name. When I was in 2nd grade, I couldn't remember my teacher's name. My pet's name. I don't have a pet. My father's maiden name. My father's middle name. He didn't have a middle name. My middle name. Well, thank you. A question I can answer. I do have a middle name. My middle name is Joy. I typed it in, Joy, and it said, not enough letters. So new rule, security questions must be specifiable by the user. I might say, or specifiable, or you should select from a very large list, but I have faith that they can come up with an arbitrarily long list of questions I won't know the answers to. Now, there was a comedian I was watching on TV that had the following joke, and I would love to credit him, but when I looked at TV Guide to figure out which comedian it was, I tracked him down, asked him for permission to quote his joke in my textbook, and he said, oh, of course I would love that, but it's not my joke. And so I don't know which comedian gave this joke, unfortunately, but it's a cute joke. So it's about, how to authenticate you based on these questions. So the comedian said that his bank required him to provide a question and an answer, and every time he called his bank, they were required to ask that question, and he was required to give that answer. So the question that he came up with, that his bank was required to ask him every single time he called the bank, was, are you wearing underwear? And the answer that he would give is, I don't think that's an appropriate question. Now, another thing is keeping user information. I do not want to do single-click ordering, whatever that is. Sounds really scary. I don't mind typing in my address. I don't mind typing in my credit card number. I prefer it because I might decide I want to use this credit card rather than that one on this purchase. Merchants insist on keeping all of this information, which is really scary when you happen to go to a merchant you haven't bought something from for 10 years. All this stuff appears. It's like, wow. And eventually this information gets stolen. So people are so concerned about, is it safe to bank on the internet because someone might be eavesdropping? No, that's not the problem. The problem is, even if you don't do things, the merchant keeps databases which are accessible on the internet, and eventually they get broken into. And the merchants say, sorry about that, but it's your problem. And they should actually have to bear all of the burden associated with it, but they don't. So new rule, after a merchant is paid, all information, any subset of the information that you want them to delete, they should be required to delete, including all of it. That is the kind of non-technical solution that would make the world so much more secure. How hard could it be to pass a law requiring this? So, summary. I guess I have sort of two joke ending slides, so I guess I'll do them both. We need protocol designers that are humble enough to learn from other protocols. There's one of the problems in standards bodies is they like to say, it's like sports teams. They say, oh, all of the other standards bodies, everything they say is worthless. We don't have to learn anything that happened before. But good engineering means you should really understand it. If things are not simple, they won't work. And then in my book on network protocols, interconnections, the last chapter, I talk about how to design protocols and things to think about. And I have little boxes there that I call real-world protocols. So as an example of a scalability issue, I talk about the wine glass clicking protocol, which is n squared. So if you have a large group of people, it's not very scalable. But everyone's favorite protocol, real-world example in that book, is that one of the problems in computer science is that people don't think about what problem they're solving. Instead, they deploy something and gradually let it grow, adding little warts to it. And so this is an absolutely true anecdote, and it will forever explain to you why you should know what problem you're solving before you try to solve it. When my son was 3, I saw him, he ran up to me, crying, holding up his hand, saying, my hand, my hand. So I took it and I kissed it a few times. What's the matter, honey? Did you hurt it? And he said, no, I got pee on it. So I suppose I will also I guess I was trying to decide which joke to end on, so I will also, the next one is sort of something that my co-author on the security book said in a talk, and it just captures the world so well. Until a few years ago, you could connect to the internet and be in contact with hundreds of millions of other nodes without giving even a thought to security. The internet in the 90s was like sex in the 60s. It was great while it lasted, but it was inherently unhealthy and was destined to end badly. I'm just glad I didn't miss out again this time. So anyway, so thank you. So I think there's time for a few questions.
Yes.
And hopefully I can understand the translation.
¿Es okay?
Yes.
Okay. Bien, muchas gracias, Radia o Radia. Francamente interesante tu ponencia y muy divertida además. Muy bien. Enhorabuena. Bien, tenemos unos 15 minutos para hacer preguntas, cuestiones. Por favor, cuando hagáis la pregunta, os identificáis de dónde venís, de qué empresa, de qué universidad y lo más breve posible en español. Ella tiene traducción directa en inglés. Sí. Levantar la mano. Están las azafatas con los micrófonos. Por aquí hay uno. Sí.
Muchas Muchas gracias por la conferencia. Y una pregunta. Con respecto a la encriptación con clave pública y privada. A partir de estos tiempos en que la informática cambia muy rápido, ¿cuánto se tardaría en implementarse?
Well, you might be asking one of two things. One is, how long does it take to do an encryption or a decryption if you don't have the key? Or are you asking how long it takes to write the code to do?
How long will it take to implement an encryption with public and private key?
To
Starting
write
from today with the information, how fast the information is advancing, and how fast the technology developing.
Well, it's quite efficient for the computer once it's programmed to do encryption and decryption. But what people tend to worry about is how long will it take to break the decryption. So you have to have keys that are long enough. And that's kind of scary when you want your data to remain secure for 30 years. Now, some people think, well, computers, if you just have enough computers, you can break anything. And that's true, but if you make the keys long enough, with a traditional brute force trying all of the keys, you could make it so that it would take, 7 universe lifetimes if every elementary particle were a Cray computer. So they're not going to have that much compute power. So I do have faith in that. But there's a very interesting thing called quantum computers, which are not faster computers, they're just different. And I'm not very worried about them because they're certainly not going to be able to build them until long after I retire. But if they were to build them, which some people say they will be able to in 20 years, other people say never, but who knows. If they were to do it, what's interesting is there's 2 very scary algorithms that could run on a quantum computer. One which breaks factoring very efficiently, which means that the RSA algorithm becomes unusable, and the other is breaks discrete log, which makes elliptic curves go away. And these are the 2 public key algorithms we depend on. So, that will make the world interesting. Now, just sort of as a point of pride, my son is a cryptographer, and he works at a U.S. Part of the U.S. government called NIST, and what he's working on are public key algorithms that will work even if they had quantum computers. So, yeah, I hope I answered your question.
Gracias. ¿Preguntas? ¿Alguna pregunta más? ¿Alguna cuestión? Nadie, los alumnos, ¿cómo es posible que no pregunten? ¿Sí? Sí, hay una por ahí.
En primer lugar, de nuevo sumarme a los agradecimientos por su espléndida charla. Y en segundo lugar, quería preguntarle acerca de si alguna vez ha tenido que ver sometidas sus investigaciones a la NSA. ¿Y cuál es su opinión acerca de las restricciones que ha impuesto a lo largo de la historia? Acerca de la criptografía, claro. Me refiero al chip clipper, etcétera, etcétera, vamos.
Yes, that is a really fun question. So, for years, the U.S. government wanted to prevent cryptography because they wanted to be able to listen to everything. And there is something to be said for that, but you can't make something that's secure against everybody except the government. So this was very annoying to U.S. companies. Oh, well, what they really wanted to do was prevent you from building it at all, but they weren't allowed to do that. So they said that you couldn't export it. So that was weird because it was the FBI, which is internal, that was forcing the US to tell their companies they couldn't export their stuff. So that really made no sense, and it was very frustrating. And it meant that US companies could not compete. So I'm probably being recorded, aren't I? Oh, well, the world will change with Obama. So US companies said, we can't compete. This is very bad. And so the US government said, not a problem. And what they did was they convinced all of the other countries to enact the same laws so that those countries couldn't export either. But then there was I think it was Finland that said, no, and that kind of made things unravel. So, thank you, Finland. But the other thing is that the rules made no sense. So, for instance, you could export SSL, but not IPsec. And so I was, complaining to somebody. I was saying, I don't understand this stuff. How is it possible that they're letting you export SSL and not IPsec? And this is even recent, so it's not like the rules have gone away. And so he said, come on, Radia, let me explain it, what export rules are like. It's like you're a puppy and you're being house trained. Sometimes when you pee, they hit you with a newspaper and say, bad dog. And other times they say, good doggy. And you have to figure out, is it because of how I was holding my ears at the time? So, it's right. Now, the one time I actually had to negotiate with the NSA for an export license, I never met the person, but I had a telephone number I would call. And he would talk to me, and apparently he found me hilarious because I kept, asking questions. So I would say, but that doesn't make any sense. It's exactly the same. And he would just laugh. So I'm glad I amused him, but it was very annoying. Now, the other thing which is fun is that my son, who works at NIST, his group does standards for cryptography. So because he's my son, I feel like I can call him up and complain to him about things. So they had this very, very complicated thing for encrypting a key. Now, to me, if you're going to encrypt a key, you take the key, you have the thing you encrypt it with, you encrypt it, end of story. But they had this horribly complicated thing. So I called him up and said, why is it you have this complicated thing? And he said, it's not our fault. It was the NSA told us to do it that way. And so I started asking him technical questions. And so I was talking to him on the phone, and he said, come on, NSA guy, you must be listening in. Can you please help me here? So, yeah, I guess that's sort of my thoughts on the export stuff.
Thanks. ¿Alguna pregunta más? ¿Alguien tiene alguna cuestión más?
Someone up there.
Up there.
Up there.
Levanta la mano, por favor. Y si te
Buenos
puedes
días.
presentar, por favor. Está bien.
Sí, buenos días, Lourdes López, de la Universidad Politécnica de Madrid. ¿Realmente crees que el uso de la criptografía de clave pública es la solución para el problema de autenticación en Internet? Yo no soy muy optimista, porque si ahora mismo olvidamos cuál es el nombre de nuestro profesor de segundo grado, por ejemplo, como pregunta, o olvidamos la contraseña, tenemos un problema también incluso con la identificación de clave pública. Y es que, al fin y al cabo, aunque usemos la carta o el DNI digital, el documento de identificación digital que se está empezando a extender en España, por ejemplo, nuestra clave secreta la tenemos que proteger de nuevo con un token criptográfico, con una contraseña. ¿qué pasa con la contraseña de nuestra clave secreta? Si la perdemos, si la olvidamos, si nos la roban. Si la sustituimos por una identificación biométrica, yo creo que la gente en general tiene miedo. ¿Qué pasa si le roban, si le cortan el dedo? Es decir, ¿dónde terminamos? ¿Cuándo encontraremos una solución al problema de autenticación? ¿Qué pasa también con los pequeños dispositivos? Se dice que el futuro de Internet ya no solamente es la conexión de las personas a través de la red, sino la conexión de los pequeños dispositivos electrónicos, los frigoríficos, las lavadoras, las cámaras, etcétera. Estos dispositivos, muchos de ellos tienen una capacidad muy pequeñita de memoria y una capacidad muy pequeña de proceso. No podemos utilizar criptografía de clave pública. Entonces, ¿cuál va a ser nuestra solución para la autenticación en general? ¿Qué piensas tú que va a ser?
Okay, so there was a lot of thoughts in there. So let me try to think of some. Yes, you're right. One of the problems with public key authentication is that users don't remember their private key. So if you had a smart card that had your private key, that would be very nice. But what happens if you lose your smart card? So I don't think that these are insurmountable problems. I think the system that I showed you before, where there's some place that has your private key encrypted with your password, and you can download it in case of an emergency, that's a reasonable stepping stone. So I think that there's ways of doing it. What I think is unfortunate is that sometimes when you have clearly the right way to do something, people think of the most incredibly obscure, difficult cases and say, oh, but in this case, it would not work. And so everyone is frozen and doesn't do anything because there are some bizarre cases where it would be inconvenient. Now, if somebody steals your smart card, it would be nice for the smart card to have biometric authentication or a PIN or something. And no matter what, like you said with biometric, if you cut your finger, maybe you can't open your smart card anymore. But in all of these cases, that would be the same as your smart card. You're leaving it in your pants pocket when you do a laundry and it breaks. So you would have to store your private key someplace else. Now, if that's for data encryption. For authentication, it's okay to change to a totally new one. You don't really need to recover the one. There has to be some way of letting all the merchants that know you by your public key know that it's a new one. But, I believe that's another whole talk that I could give about how to make public key much more convenient. But why? I don't think any of these problems are that hard. So why is it that the world hasn't done it yet? Well, part of the problem was that for a long time after the concepts, there was a patent on RSA. And the patent holders on it were making it so expensive to license it that they basically crippled the industry. But now that it has expired, people have lost enthusiasm and lost momentum. One thing that I think is sort of sad is that people are now just saying PKI failed. But once everyone says that, your customers believe it, and it's harder to sell them on doing it. And then there's a whole bunch of people that say, oh, PKI failed. What we have to do is reinvent everything and encode it in XML instead. And it's, it wasn't the problem that the encoding was too efficient and we needed a less efficient encoding, because that's all XML does for you. So yeah, I'm not sure whether, I think there were some other questions you asked that I didn't get to, but those were the ones I remembered.
Una última pregunta más. ¿Tenemos tiempo? ¿Alguna cuestión? ¿Alguien? ¿No hay nadie? Bueno, entonces voy a hacer una pregunta.
Wait, there's one up at the
there's one?
top.
Okay.
Oh, okay.
Sí, arriba. Right there.
Pedro García, de Telefónica. Doctora Perlman, creo que es un honor para todos haber escuchado su conferencia. Quería hacer una pregunta un poco más filosófica, quizás, no tan técnica, y es la siguiente. Estamos hablando de autenticación, de método de autenticación, protocolos, claves simétricas, claves asimétricas. ¿No cree que quizá también hay una falta, digamos, de concienciación en el sentido de querer proteger la información? Porque creo, mi impresión es, que la mayoría de la gente fuera quizás de este ámbito, de ámbitos tecnológicos o académicos, la gente no se conciencia de que hay información que es necesario proteger y que es necesario protegerla hasta qué punto. Un poco por ahí va mi pregunta, si quizás conoce usted, si se observa alguna tendencia en el sentido de que la gente utilice más la criptografía, la utilice menos, concienciación también por parte de la gente. Gracias.
Yes, there's definitely a trade-off between convenience and protecting things. So, well, one example was that when my son was a baby, he was just a few weeks old, I drove someplace with him in the back seat, in the car seat, and it was a warm winter day. So I got out of the car and I decided, I don't need my coat. So I took my coat, I put it into the car, and I locked the front door without realizing I had put my key into my coat. So now I had my baby locked in my car on a sunny day, and you hear, oh, wow, within 5 minutes, if the sun is there, the temperature gets to be 9,000 degrees. So I was panicking. I had no idea what to do. And this 12-year-old kid wanders by, and he said, "What's the matter, lady?" Because he could see I was upset. And I said, "My baby, I locked it in the car." And so he said, "No problem." And he knocked on the nearest door, got a coat hanger, and got into my car in like 5 minutes. And I was thinking, why am I locking my car if any 12-year-old kid can break into the car? So I kind of stopped locking the car. Also, I really hate locking my house. And so, again, there's this trade-off between doing all of this encryption and making it all just very easy. And you won't bother with a burglar alarm until you've been burgled. So, yes, there's a lot of information that really matters for privacy that people don't think that it matters. There's things like GPS systems in cars that could be used for good or for bad. If there's some database that knows everywhere your car went, you might be able to get your car if it got stolen, or you might be able to prove you're innocent. But it's, that's just a philosophical question, and I don't have good answers about that. Yeah.
Okay, bueno, me parece que estamos en el tiempo. Ha sido un placer contar con Conferencia Radia. Y además de una persona, como veis, experta en temas de seguridad, es una encantadora mujer. Muchas gracias por estar aquí. Bueno, a continuación, la doctora Radia Perlman tendrá una rueda de prensa con gente de periodistas. Si hay periodistas aquí, que sepan que la doctora saldrá de la sala con dos compañeros de la cátedra, con Carmen y Alfonso, y tendrá una rueda de prensa de una hora más o menos aproximadamente, y luego se juntará con nosotros en el cóctel, con lo cual si alguien quiere luego hacerle algún tipo de pregunta más personal cuando estemos en el cóctel, pues encantada de responder. Muchas gracias, Radia.
Thank you. Mm.